I just wanted to have this slide basically advertising machine learning. I guess most of you probably come from machine learning area, but you know it's a remarkable field because over the last decade, machine learning had a huge impact on a variety of fields, and computer vision, information retrieval, speech processing, robotics, computational biology, and it's really exciting. And most of the talk, I'll show you some applications, in particular in computer vision and speech processing, information retrieval as we go through the talk. And one other thing that I wanted to mention before we start getting into specific details is over the last decade, or actually over the last 5 or 6 years, we've been experiencing a huge boost in the amount of computational power as well as the amount of machine readable data. Right? We have data coming from us in terms of images, text, speech. This is an interesting area. Collaborative filtering or product recommendation systems. There's the social networking data, scientific data. And what I should emphasize is that most of the data that we see today is what I would call mostly unlabeled. So that basically means that you may have access to lots and lots of images, but you may not necessarily have access to labels of what's going on in those images. So I can go on the web and download lots of text, but it's very hard to get annotations or labels for specific things. So what we should be looking at is, at least in this talk, I'm going to be trying to develop statistical models that can discover structure or can look at the underlying statistical relations in unsupervised, what's called unsupervised, or semi-supervised way. And a semi-supervised way basically means that you might have partially labeled data, a few labeled examples. So how can you use those? And also, it's important also to keep in mind how can we build models that can be applied in multiple application domains, right? Models that can be used in a variety of these fields. That's my interest. And in this talk, I'm going to be looking at one particular framework of doing that. And I'm going to be looking at deep generative models that support inferences as well as discover structure at multiple levels of representation. Okay. Now, before I get into any specific details, I wanted to show you a couple of models and what they can do. So this is a particular model called Deep Boltzmann, something that I'm going to be talking about in the second part of the talk today. You know, you have lots of latent or hidden variables, so probably you should be familiar with those as we go through the summer school. And you're looking at images. These are 96 by 96 images, and what we're trying to do is we're trying to model the distribution over these objects, these cars, airplanes, and such. And these latent variables, these are stochastic binary latent variables, so some of them are on, some of them are off. And because this is a generative model, we can generate data from this model. So this is what the model believes images of airplanes should look like. Right? So here you're seeing that the model does a pretty decent job in terms of exploring a space of possible airplanes. And it does a fairly good job in terms of looking at different airplanes. Notice how it morphs from one airplane to another airplane and such. And these are fairly high-dimensional data points. We've also been looking at something simpler than that, which is a model of handwritten characters. So this is the data that was collected at MIT. These are handwritten characters. They come from 50 different alphabets around the world. You have Arabic, Cyrillic, Sanskrit, and such. And again, because this is a generative model, we can ask the model to see what it believes Sanskrit should look like. And this is what the model believes Sanskrit should look like. A lot of these characters, they do look like Sanskrit characters. Some of them don't. But again, the model is able to capture interesting structure in the data. Okay, and you have these 28 by 28 images. You have about 2 million parameters in these models. And it does a fairly good job in terms of exploring what Sanskrit characters should look like. So it has some notion of understanding what Sanskrit looks like. We can also do interesting things like pattern completion or what's called conditional simulation, right? So here, if I show you part of this image here, right? This is what the model believes the remaining part should look like. And again, it captures a lot of interesting structure in the data. Right? It does a fairly good job in terms of completion here. And you can obviously see how that might be useful in computer vision applications. Now, why building these models is difficult? Well, if you look at 28 by 28 image, right, there are 784 possible pixels here. Well, if you look at the space of all possible images, that would be 2 to the 784 possible images. That space is huge. Okay? So the question now comes, how can we build models? Obviously, we'll have to do some approximations. A lot of these models, we have to do approximate learning and approximate inference. But how can we efficiently learn these models, in particular exploring this high-dimensional space? Right? Now, so far, again, I haven't given you any specific mathematical details. As we go through the talk, we'll go there. But these types of models can be applied to other sorts of data. So here is a data set of word counts. These are web pages coming from the Reuters data set. There are about 800,000 of those. And if you're building this model and you look at the structure, the low-dimensional structure that it discovers, this is the type of structure that it discovers from the data, right? And it's done in a completely unsupervised way. So we didn't tell the model that these documents belong to, internal markets and so forth. It just discovers the structure on its own. And it's interesting, I always like to point out that it finds that European community economic policies are next to disasters and accidents, right? So it's happening here. That was collected, the data set was collected in '96. Yeah. I guess nowadays it'd be these two things will just get closer together, right? So what that means is that if you're using these types of models for information retrieval, right, so occasionally you'll be mixing up the two. Okay, so what we're going to do is I just wanted to give you the talk roadmap, or the talk outline, what we're going to be talking about today. First, I'm going to spend some time, maybe about 10-15 minutes, just looking at the introduction as well as looking at graphical models, right? Because we're going to be looking at deep networks from graphical model perspective. I'm going to briefly go over restricted Boltzmann machines. I'm sure that you've heard about restricted Boltzmann machines through the summer school by a number of speakers. And I'm also going to talk about deep belief network in terms of learning park-based hierarchies and such. So that's going to be the first part of the talk. And the second part of the talk, we're going to look at a more advanced model called deep Boltzmann machine. And particularly, we're going to be focusing on inference and learning, as well as I'm going to also look at several extensions, more advanced deep models. Okay, so that's going to be the plan for today. Okay, so here let me just give you a couple of slides on what the inference problem is. It's pretty standard. Suppose we have some data set, we have some data, right? Typically in Bayesian statistics, and we're going to be using Bayesian statistics in the talk here, we're going to be looking at the posterior distribution of parameters, right? We have to specify the likelihood function, which is a function of the parameters theta. We have to specify the prior probability of the parameters, and then the goal of the inference is to compute the posterior distribution of the parameters. This is known as the inference problem. So typically when we talk about deep networks and we're saying, well, what are the latent variables given an image, what are the latent variables that represent that image, we're going to be doing inference. We're going to be computing posterior distribution over the parameters. Now, unfortunately, computing this denominator requires us to integrate or sum out over exponentially many terms, and typically that integral or the summation is pretty high dimensional, so it's difficult to compute. That's something that we have to deal with. Now, in general, also, when we're going to be looking at predictions in Bayesian statistics, given some data, we're going to be computing the conditional distribution of a new data point, condition on the data, and that would require us to compute this integral as well, right? We can write it in the form of expected value with respect to the posterior distribution, right? And this is sometimes called predictive distribution. Now, the issue computing predictive distribution is that we need posterior distribution. And to compute the posterior distribution, we need the marginal likelihood or the normalizing constant, right? Now, as I mentioned before, computing the marginal likelihood will often be dealing with high-dimensional integration over high-dimensional spaces, or computing the posterior distribution. Predictive distribution is often analytically intractable. So something that we have to deal with. In fact, a lot of Bayesian statistics and a lot of models that I'm going to be talking about today, generative models, all of them have something in common, which is trying to integrate or sum over huge dimensional spaces. How can we do that efficiently? Okay. So let me just give you, how many of you know about graphical models? Can you raise hands? Oh, okay, so most of you know about graphical models. So let me just, for the sake of notational, as we go through notation. So graphical models, these are pretty powerful framework for representing dependency structure between random variables. You can specify the joint probability distribution over a set of random variables. Typically, when I'm going to be talking about graphical models, you will see a set of nodes representing random variables, and you'll have a set of links that will represent dependencies between those random variables. Okay? And typically, when we talk about graphical models, we'll make an assumption that the joint distribution over these random variables, it decomposes into the product of factors. And these factors will depend on the subset of random variables. So it specifies certain independence properties, the graphical models. Now, there are two types of graphical models, which is quite important. There are directed graphical models. These are called Bayesian networks. And there are undirected graphical models. These are called Markov random fields, or Boltzmann machines. And there are other types of graphical models called hybrid graphical models. And these are the models that combine directed and undirected models. Now, you have to be careful how you deal with these problems when you start defining hybrid graphical models, because sometimes they become incompatible. So, for example, a deep belief network is a hybrid graphical model. And tomorrow I'm going to talk about hierarchical deep models. These also would be hybrid graphical models. Okay? So just, again, just for the notation, directed graphical models. In the directed graphical models, you specify the joint distribution over the variables conditioned on the parent. So you have a product of conditional distribution for each node conditioned on its parent. So for example, if you look at the joint distribution over these random variables, you can write down the joint distribution in this form here, right? You have P of x1, P of x2, P of x3, and then probability of x4 here. Probability of x4 is going to be dependent on x2, x1, and x3, and so forth, right? So this would specify directed acyclic graph, or DAG. Now, this is one particular example as being used in computer vision communities. Computer vision people like directed graphical models. The idea is that here you define a generative model of an image. How do you define the generative model of the image? Well, you might have an object identity, which might be a discrete random variable. You might have position and orientation. Those could be continuous latent variables. And they will have independent prior probabilities. And then the image itself has a probability distribution that depends on object identity, position, and orientation, which we will call the likelihood function. Right? So here, the joint distribution over the image as well as these latent variables can be formed as a likelihood function, conditional probability of the image conditioned on object, position, orientation, times the prior term. Right? So this is a very simple directed graphical model. Now, in general, what we're going to be doing is condition on the image. We would want to know what's the image identity, where its position and orientation and such. In which case, we need to compute the posterior distribution over these latent variables. And again, the posterior distribution has this form by Bayes' rule. And this is where we have a problem, right? Computing the marginal likelihood. It's often very difficult to compute, right? So a lot of efforts in statistics and machine learning is being dedicated to how can we compute these marginal likelihoods, right? Some of the popular models that I want to briefly mention, one of the popular models, directed graphical models, is latent Dirichlet allocation, something that I will be talking about in tomorrow's lecture. It's a fairly widely used model. And the second model is probabilistic matrix factorization. Again, it's one of the popular models for collaborative filtering applications. It was part of the winning solution in the Netflix contest. And again, you can see that both of these models are directed graphical models. Okay, so let me just give you an example of probabilistic matrix factorization. Suppose we have a matrix of this form and we factorized as a product of two low-rank matrices, right? So we have end users and end movies, and we may have integer valued ratings, and then a particular rating for user I and movie J can be represented as a product of users and movie feature vectors. So in this case, all we're doing is we're trying to approximate this matrix, very sparse matrix, as its low-rank approximation. Okay, and the goal is to predict missing values. So again, this is a fairly standard problem in collaborative filtering. You know, you can define a fairly simple model, a bilinear graphical model. It's a directed graphical model. You can place Gaussian prior over your parameters or use a movie feature vectors. It's not really important that these are Gaussian and whatnot, but here we just specify the likelihood function, how ratings are formed. We specify the prior probabilities over the latent factors. We can also specify the hierarchical prior. We can introduce Gaussian Wishart prior. We use a movie hyperparameters and such. So again, we can build a fairly complex directed graphical models. And again, if you look at the literature, you know, you have a very standard model. You can extend this model. You can start building more and more structure into your prior and such. And you can make your model more and more complex by basically adding more nodes and drawing more errors here. But now, if we're interested in making predictions, for example, right? In this case, to make a prediction for a new rating, we need to integrate over all of these parameters and hyperparameters. And this is where the problem comes in, right? These integrals are typically high dimensional because we have to deal with high dimensional latent variables here. And so exact evaluation of this predictive distribution is typically analytically intractable. And if you look at the posterior distribution, it's fairly complicated. It doesn't have a closed form expression. So just to make a point, once we start looking at deep networks, in particular deep Boltzmann machines, we're going to have to deal with something similar to that problem, computing these posterior distribution over latent variables. Right? So we need to approximate. Now, there are two options. One option is to use factorized distribution, or to use what's called variational framework, variational inference. Something that we're going to be using, so I'm going to have to make a small introduction to variational inference as well. The other option is to resort to Monte Carlo methods. And you will hear about Monte Carlo methods, I guess, on Thursday and Friday, or Wednesday, Thursday, and Friday. So we're going to be a couple of lectures on Monte Carlo methods. Okay? Now, let me jump into, so these are classes of models called directed graphical models. Let me just briefly talk about undirected graphical models. These are Markov random fields. Markov random fields, you specify it as a product of potential functions. So it has quite different interpretation. You have a product of potential functions, and each potential function, you can think of it as a mapping from the joint configuration of random variables to a non-negative number. And the choice of potential functions doesn't really have to have probabilistic interpretation, unlike in directed graphical models where you have to specify the conditional probabilities, right? So typically, potential functions will be represented as exponentials. So the product of these potential functions will typically be writing them as e to the negative what's called energy, right? So in literature, sometimes the most commonly used form is you specify the energy of x, and then you look at the probability of x. This is also known as a Boltzmann distribution. Hence, as we start talking about Boltzmann machines, we're going to be using that notation here. Now, why these models are also tricky to work with? Well, suppose we have a binary random vector, right, that takes values +1 or -1, just like the binary images that we've been looking at. If x has only, let's say, 100 dimensions, then we need this normalizing constant. We need to sum over 2 to the 100 terms, right? And that problem basically becomes fairly complicated once we start working with high-dimensional data, with images, high-dimensional images. Again, this normalizing constant will give us a lot of problems. We have to deal with that somehow. So computing this normalizing constant is often very hard, and if you look at undirected graphical models, this represents a major limitation of undirected graphical models. A lot of research is being done in terms of how can you estimate reliably what these normalizing constants are, or even how can you estimate reliably the derivative of the log of the normalizing constant, which we will need for learning. Okay, and if you look at, compared to the computing the posterior distribution, it has a similar form, right? Basically, here you have to do integration of a high-dimensional, you have to perform high-dimensional integral. Here you have to sum over exponential many terms. So a lot of these problems have the same common problem as to how can we sum out or integrate over high-dimensional spaces. Now, as we go through the deep networks and such, we're going to be looking at the maximum likelihood learning. So here's the maximum likelihood learning for binary pairwise Markov random field displayed here. We can specify the probability of x in this form. Here we have xi, xj, where I and j belong to a particular edge, and theta ij, these are the parameters that's sitting on these edges, and these are just bias terms. Now, given a set of ID training examples, we want to learn model parameters, right? So what we want to do is, one option would be to maximize the log likelihood objective, which is a standard option. And the log likelihood objective has this form, which has a fairly intuitive form. It essentially says that what we want to do is we want to maximize the probability of the joint configuration of all the data points that we're observing, right? If you take the log, then it just becomes sum. Now, if we look at the derivative of this log likelihood function, we just plug this in here and differentiate with respect to parameters of this model, then we have a difference between two terms. Okay, it's fairly simple to derive. The first term is easy to compute. These are just count statistics. Effectively, you're just seeing how many times xi takes value 1, xj takes value 1. Xi takes value 1, xj takes value -1, and so forth. These are just counts. Now, this term here is expectation with respect to the model distribution, right? And this thing here is difficult to compute. right? Remember at the very beginning of the talk when I showed you the generative model, and I was saying that when you will look at all possible images that the model could generate, that space is exponential. Well, we have to deal with that problem here as well, right? So this is generally difficult to compute. Now, once we get into more advanced models, Markov random fields with latent variables, then things become much more complicated as well. So suppose that we have random variables, and random variables will contain both visible and hidden variables, right? So this is an example of a deep Boltzmann machine where we have observed variables. You can think of them as pixels in the images, and we have latent variables. Now, the probability of observed input can be written this way here. Again, we have to deal with the normalizing constant, but then now we have to sum out over all latent variables here. And typically, this summation becomes intractable as well. So now we have two sources of intractability. One is the normalizing constant, and the other one is this summation, right? And computing the partition function, summation cannot be done explicitly or analytically, and then parameter learning these models becomes fairly tricky. And deep networks have to deal with that intractability. Okay. Now, just coming back to the inference problem, in a lot of problems that we're going to be looking today, we're going to be looking at computing these expectations. We're going to be looking at computing expectation of some function of z, and we have some probability of a z, where these integrals are typically high dimensional, and if we're dealing with discrete random variables, the integrals will be replaced with sums, right? And we'll often be using the following notation. We're going to be looking at the probability of z as a ratio of probability tilde of z divided by the normalizing constant. We can evaluate the numerator point-wise, but we can't evaluate the normalizing constant, right? So if you look at, for example, in Bayesian statistics, computing the posterior distribution, the denominator we can't compute. If we look at Markov random fields, we can compute normalizing constants, okay? So all of these problems can be lumped together into one problem as to how can we estimate these expectations, okay? Now, there is one other piece that I wanted to point to is variational inference, something that we need to know and something that you should know about. It's a fairly simple idea. If we have to approximate the posterior distribution over the parameters conditioned on the data, right, typically this posterior distribution can be very high dimensional, can be fairly complicated. But what we can do is we can replace this posterior distribution or approximate it with a simple tractable distribution Q. So for example, we might want to approximate with a Gaussian distribution, something fairly easy we can get our hands on, right? Now, the variational inference framework relies on this one equation. So if you understand this equation, you roughly would understand what variational inference does, right? The idea here is the following. If we look at the marginal likelihood of the data, we can basically write explicitly, this is the likelihood function, this is the prior. We can multiply and divide by the Q function. So I haven't really done anything here. And then all we have to do is we can use what's called Jensen's inequality. And the Jensen's inequality essentially pulls this log inside here, right? And this is what happens. And now we can simply write this expression into what's called expected complete data log likelihood and the entropy function. And this is known as a variational bound. Okay? You can also write it as a log of the normalizing constant minus what's called the KL divergence, Kullback-Leibniz divergence between the approximate distribution Q and the posterior distribution P, right? And the KL is a non-symmetric measure that essentially it looks at the distance between two distributions, right? It's defined this way. What the variational inference attempts to do, the variational inference attempts to maximize this variational bound. It tries to make this bound as tight as possible, okay? So notice that in this expression here, there is nowhere we see probability of the D. So we don't see this thing here, right? Typically, these integrals can be done in closed form, depending on your Q distribution. If Q distribution is fairly simple distribution, we can evaluate these things. And what we're going to be looking for, we're going to be looking for the Q distribution that maximizes this bound and makes it as tight as possible. And this is a general principle of variational inference that you should have in mind. Basically, I want you just to remember that you're trying to approximate the complicated distribution with a simple distribution. Okay? In particular, one common approximation that's being used a lot, and that's what we're going to be using, it's called mean field approximation, where you're saying that the approximate distribution Q factorizes into the product of factors. Right? So if you have D-dimensional problem, you have D latent variables, you're basically making assumptions that they all become independent. Okay? And as soon as they become independent, it's much easier to deal with that problem. And in this case, if you just plug this approximation into variational lower bound, entropy term you can compute, just factorize this into the sum. This piece here you can compute as well. Now in general you can start optimizing with respect to these Q distributions. What you can do is you can keep all of the Q distribution except for one of the factors and maximize the variational bounds with respect to the Q of j. So it essentially does, what it does is you write it as a product of factors and then you optimize each factor one at a time. So there is an iterative procedure. Right? And it turns out with a little bit of algebra you can find the optimal Q distribution conditional on all the other factors, and you can define an iterative procedure and you have certain convergence guarantees. Right? So one thing I want you to have in mind is that if you look at this example, the yellow thing here is the original distribution. Right? So the original distribution doesn't have a closed form solution. And the red is what's called Laplace approximation that I didn't really talk about, and the green is the variational approximation. So it does, it doesn't do it too bad of a job in terms of approximating it, the posterior distribution. Okay. Okay. Now we've sort of looked at the basics of graphical models. We've looked at directed and undirected graphical models. We've looked at the variational inference. So let's quickly go through restricted Boltzmann machines and deep belief networks and some math behind these models, and really try to look at these models from graphical model perspective. Okay, restricted Boltzmann machines. This is something that you probably know, as a number of speakers probably talked about it. But just to reiterate, we have stochastic binary visible variables V. These typically binary, line D-dimensional space, that are connected to stochastic binary hidden variables. So if you think about an image, you can think of each pixel here, these nodes representing pixels, and you can think of H's or latent variables as detecting certain patterns in the data, certain structure in the data. We can define the energy of the joint configuration. This is an undirected graphical model. So we define the energy. The most important term is this term that looks at dependencies between observed and latent variables. And throughout the rest of the talk, by theta, I'm going to be denoting the model parameters, the parameters that we're going to be trying to learn. Okay? Now, the probability of the joint configuration is, again, going to be given by the Boltzmann distribution that has this form here. Or you can write it in terms of products of potential functions. So if you need conversion between graphical, undirected graphical models and restricted Boltzmann machines, that's what's happening here. You can, again, write it as in terms of graphical model formulation. And we have a partition function or normalizing constant. And these are Markov random fields, Boltzmann machines, log linear models. They have different names, but this is the most general form of defining these models. Okay? Now, there is another interesting interpretation for that particular undirected graphical models. It's called product of experts formulation. And the reason why it's called the product of experts formulation is that if you sum out the states of the latent variables, in that particular model, you can perform the sum explicitly, analytically. Then once you sum out the states of the latent variables, you have this form, right? You have a product, and these are what's called experts, right? So by summing out over the latent variables, you end up by multiplying a bunch of factors together, right? Now, why these models are called restricted? Well, they're called restricted because there are no connections between latent variables, okay? And this has advantages and disadvantages. The key advantages is that inferring the distribution of a latent variables or hidden variables can be done in closed form. And this is very important for applications such as recognition or information retrieval, right? I show you an image, and I can instantly compute what are the latent factors that make up that image, right? Or if you give me text, I can instantly tell you what latent topics that make up that text, right? So that can be done quickly in closed form solution. And similarly, if you can compute the conditional distribution of observed image condition on the latent factors. So if you give me the latent topics, I can generate the text. Or if you give me the latent features of an image, I can generate the image. Now, in terms of learning the features, you've probably seen that as well. If I give my model or restricted Boltzmann machine these types of handwritten characters, this is the type of structure that it learns. These are all edges and such. And the way to think about these models is that if I show you a new image, I can decompose it in form of these edges, right? Where these numbers are given by the conditional probabilities of latent variables, conditional and observed variables, right? So it essentially, you can think of it as a basis decomposition. This is a standard way of displaying it. And obviously, you can see that observing something like that in that image would have low probability. Okay? And now you can represent this new image in its conditional form. And that forms the basis for all the deep models where you start stacking these things together. Now, and it's easy to compute. Now, in terms of model learning, again, if you see a set of ID training images and we want to learn model parameters, then we can maximize the log likelihood objective. Typically, we end up maximizing penalized log likelihood objective, where you have some regularization term, right? Again, if you look at the derivative of this log likelihood objective with respect to parameters wij, with respect to these interaction terms here, the algebra is pretty simple, and it comes down to, again, the same difference between two expectations. The first is the expected sufficient statistics with respect to the data distribution. The second one is expected sufficient statistics with respect to the model distribution. Now, for restricted Boltzmann machines, and that's why a lot of people like these models, computing this first term can be done in closed form. Okay? Just like in standard Markov random fields. Because the probability of the data is given by the conditional probability of latent variables, conditional and observed variables, times the empirical data distribution. So again, this can be done in closed form. This is where we run into problems. But this is the same problem as for any undirected graphical model. Okay? And again, there is a lot of work, in particular in statistics and machine learning, looking at various ways of approximating these expectations. Now, one common way that in our community, in deep learning community, people are approximating these expectations is using contrastive divergence, right? And contrastive divergence is Markov chain Monte Carlo based approximation, but it's a very simple approximation, very intuitive approximation. You start with the data, you sample the states of the latent variables. You can do it in closed form, right? Because you have closed form solution. These are just given by sigmoid functions. You reconstruct the data. And then you infer the states of the latent variables, and then you just look at difference between two expectations here, right? Again, this can be done using stochastic Monte Carlo approximation. Now, in general, the right way of approximating these expectations would be to run this Markov chain. It's called the Markov chain. You'd run this Markov chain up to infinity, and then you would start collecting samples from your from the model. And contrastive divergence basically says, well, instead of running your Markov chain up to infinity, just run it for one step. Okay? So that's what it does. Sounds silly, but it works remarkably well. Now, and this is just a standard. You've probably heard about contrastive divergence and such. Now, there are other types of graphical models, restricted Boltzmann machines, where you can extend them to other types of distributions. So for example, if you want to model images, then you can define the energy function in this way, and in such a way that the conditional distribution of these observed data points or observed pixels would take Gaussian form. So you can model real valued data. And the conditional distribution of the latent variables would still be Bernoulli random variables, or would be binary random variables. So by defining different forms of energy functions, you can look at different modalities. You can work with count data, you can work with real valued data, or any type of data that sits within the exponential family models. Okay? You can also interpret restricted Boltzmann machines in terms of mixture models. So many of you probably know about mixture of Gaussian models. And again, you can write the probability of observed variables as in this form here, where P of H is what's called an implicit pri that you get by summing out the states of the observed variables. And this is just given by the Gaussians, right? So you can think of, again, you can think of restricted Boltzmann machines as a mixture model, but here you have exponentially many mixture components with tight parameters. The reason why I have exponentially many components is because for every single instantiation of latent variables, so imagine you have 3 latent variables here, there are 2 to the 8 possible configurations, right? If you had 1,000 latent variables, you would have 2 to the 1,000 possible configurations. So you would essentially have 2 to the 1,000 possible mixture components in your mixture models. With shared parameters. If you apply these models to these tiny images, these are images of downloaded from the web, this is the type of structure that it finds. Again, you can think of each image can be represented as a linear combination of a subset of those images, of a subset of those filters. It does a pretty good job in terms of discovering interesting filters. If you apply exactly the same model to modeling text, this is the type of features that it discovers. These are topics, right? So you see there are topics about Clinton and US, and there is one about Russia and Soviets and such, and there is one about stocks and such. So it does a pretty good, and again, for different modalities, for images, you're discovering these features, right? For text, you're discovering these topics. So you can represent a particular document as a linear combination of these topics, essentially. Okay, speech is another example. I just wanted to show you, this was done by Hong-Lek Lee at Stanford, where, you know, if you look at first layer bases, and if you look at the actual phonemes, you know, there is some association as to what the phonemes represent that people found versus what the model learns. So your model learns various examples of a phoneme and such. And you can do a lot with speech recognition. In fact, I should probably emphasize that the speech community is completely now turning upside down because these models work remarkably well for speech recognition. You can also use it for collaborative filtering. This is one example where you're trying to build recommendation systems and such. Again, it's the same model, but here each observed variable is representing ratings, right? It's 1 of 5 ratings. And if you look at the Netflix data set, if you look at these latent factors, these are the learned genre or the learned topics that it discovers. And I should emphasize that Michael Moore gets its own latent variable here because his movies are very unique. So, and you find, you know, these scary movies, these are action movies, these are like comedies and such. So again, it finds interesting type of structure in data. And again, if you look at video, if you look at motion capture, speech perception, you're applying the same learning algorithm, but you look at multiple input domains. And that's what's so exciting about these types of models, because you develop it for one particular domain, but it works remarkably in a variety of application domains, in vision, text, collaborative filtering, speech, motion capture. Now, of course, there are also limitations on the type of structure that can be extracted by a single layer model, right? And so far, we've been looking at restricted Boltzmann machines. These are fairly simple graphical models. And you're only discovering sort of low-level features. You're only discovering edges, right? Or you're only discovering first-order correlations between words. Or you're only discovering first-order correlations between movies and such. And obviously, there is a need to go beyond that. And that's the whole theme of I guess, of the summer school. So let me just finish off quickly with deep belief networks, okay? What's the idea behind deep belief networks? Well, if you look at restricted Boltzmann machines, right, you're finding these edges, these are low-level features. But these low-level features, once you start building higher-level models, once you start introducing dependencies between latent variables, maybe you start capturing higher-level features. And higher-level features could be representing things like combination of edges, or something more abstract. And the idea is that internal representations can start capturing high-order statistical structure in the data, right? The intuition you should have here is that these latent variables, these hidden units, they detect certain patterns in the data, or they're looking at the correlations in the data. And these latent variables, they start looking at correlations between these latent variables, right? So you start looking at correlations over correlations and such. So the hope is that you might start getting much higher statistical, extracting much higher statistical structure from the data. Okay? Now, a deep belief network, I just wanted to give you a precise mathematical formulation of what these deep belief networks are. You can specify the joint probability distribution over the observed variables. This could be pixels or word counts or movie ratings, whatnot. You can represent it as a restricted Boltzmann machine that sits at the top, followed by what's called sigmoid belief network. So here you see that this model is truly a hybrid graphical model. It has a restricted undirected graphical model sitting on top, followed by a directed graphical model, right? So obviously now you can see how you would generate data from this model. You would sample the data from this restricted Boltzmann machine, followed by top-down pass from this model, right? So the probability of H3 and H2 here is given by restricted Boltzmann machine, and then the conditional probabilities are given by just conditional probability of H1, condition on the parents, and the observed data is given probability of observed data given its parents. Okay? So again, that's a fairly unique model, a deep belief network model, hybrid model. There is a way of pre-training this model in stages, and you've probably seen that. Just wanted to emphasize that again. You first learn the first layer RBM, then you treat the inferred values latent variables, the hidden variables, as the data for training the second level RBM. You train the second level RBM and so forth, and you proceed to multiple levels. Once you do this greedy training of restricted Boltzmann machines, the resulting model is this hybrid graphical model. Okay? Now, one interesting thing, one exciting thing about these deep belief networks, so one question you might ask is why these deep belief networks have become fairly popular at least in the machine learning community. From my perspective, one of the interesting aspects about this model is that as you start greedily pre-training these models, you can show that you can improve the variational bound on the data. So it's not that something they just throw together that works. There is an objective function that you're optimizing, and there is fairly substantial math that goes behind pre-training these models. So the idea is that if you look at the log likelihood of observed data and you look at the variational bound here, and where Q is your approximating distribution that approximates the posterior distribution over these latent variables, you can decompose into likelihood term, a prior term, and you can improve this variational bound by replacing the prior term by second layer RBM. So unfortunately, I don't have time to go specifically into details, but a lot of it is based on very simple variational arguments, variational bound arguments. What I do want to emphasize is that the interesting thing in this work that was done by Hinton in 2006 was that they've managed to show that as you add more layers into the model, you can improve the variational bound. So you can optimize the objective function. That wasn't known before. Okay, so it improves the variational lower bound. Now, let me just quickly go through a couple of applications just to show you. One interesting thing is that you can use deep belief networks for classification, obviously. So you've probably seen that. You can pre-train a stack of restricted Boltzmann machines, and you typically could convert them into standard neural networks, right? And this is done by a very simple conversion of restricted Boltzmann machines to deep belief networks into neural networks, and then you can fine-tune this model using backpropagation. And you can do a fairly good job in terms of classification. The other interesting thing is that you can use these models for regression as well, right? And in particular, this is one example where we've looked at trying to predict the orientation of the face. So here you have the training data, these are faces of people, and here you're seeing the orientation, these are labels. And this is the test data. Now, if we had training data with 1,000 image patches, of 30 different people, and then a test data contains 10 new people, and we just want to align the faces, right? That's a fairly standard task. If you use Gaussian processes, these are fairly powerful tools for doing regression, then you can achieve root mean squared error of about 16 degrees. So roughly speaking, you can predict up to 16 degrees the orientation of the face or of a new face, right? But what if we actually did the following? What if I said, well, I actually have 12,000 unlabeled data, because labeling is hard, right? Like basically trying to label the orientation of the face by hand, it's a hard task. But suppose I also give you 12,000 unlabeled faces. These are just, it's very easy to get those faces, right? Now, if you train a stack of restricted Boltzmann machines, and when you're pre-training these models, you don't have any particular task in hand that you're going to be trying to predict the orientation of the face. All you're trying to do is you're trying to learn a good generative model of a face. All you're trying to do is to figure out what faces look like, what makes face a face, right? Now, if you look at learning the stack of restricted Boltzmann machines, and you apply exactly the same Gaussian process on top of learned features here, you improve on root mean squared error. If you do, if you fine-tune the covariance kernel of a Gaussian process, so you use backpropagation to fine-tune the entire network, you go down to 6 degrees. So you can basically improve a lot in terms of predicting the orientation of the face by using this extra unlabeled data, right? And this is sort of the whole theme of what people are trying to do. The idea is that if you have unlabeled data, maybe you can try to build a good generative model of the data and understand what the data looks like. And then if you have few labeled examples, you can learn a good recognition or classification model or regression model, right? Another class of models used for compression, these are autoencoder models. And the idea is quite different. The idea here is that you go from high-dimensional data to some low-dimensional code. In this case, you go to 30-dimensional space. So you're trying to compress the data. And you can also train a stack of restricted Boltzmann machine. This is standard. You can convert it into the deep autoencoder model. This is just, again, a neural network, but that has a bottleneck layer. And you can fine-tune the whole model. And this is what we did for the Reuters data set. This is the type of structure. This is, if you compress the data down to two-dimensional codes, this is what it discovers. I've shown you before. And this is latent semantic analysis. For those of you who are familiar with standard tools that people use for information retrieval, these are the latent semantic analysis. Basically, it's a singular value decomposition model. Or you can think of this as a linear version of this model. This is a non-linear version of latent semantic analysis. So again, and in terms of information retrieval, if you're looking at precision recall curves, we can do much better compared to LSA, as well as latent digital allocation models. There is another interesting model here, which came up by looking at these autoencoder models. And the idea is that, well, what if you learn to map data down to, let's say, 20-dimensional binary codes, right? If you map the data to the binary codes, then you can do a very efficient retrieval. You can do very efficient search, right? You can think of these 20-dimensional binary codes as representing memory addresses, right? And then you can just retrieve items in the nearby addresses without doing any search at all. So you can, for example, map your documents into the memory, semantic memory address space and do retrieval, fairly fast retrieval. So just to give you an example on Reuters dataset where you have about 800,000 news stories, retrieving a particular neighbor's given new query, retrieving few neighbors takes about, I think, 0.01 of a millisecond or something like that. So much faster than you blink your, I think if you blink your eyes, it takes about a few milliseconds, so it's much faster. And people in the computer vision community picked up on this idea of looking and retrieving images, right? So you're taking your images, you're compressing them down to low-dimensional codes, and then you're doing retrieval. This is the work by that was done at MIT by Fergus, Toralba, and Layerwise, where if you show a query images, these are the similar images that you retrieve using binary codes. You can also do other things. You can also try to learn similarity measures, so similarity metrics between two inputs. So for example, if I show you these two images and I told you that they should be the same, or they should lie close to each other in the latent space, this is the type of structure that it discovers, right? And this is compared to a lot of other methods that's been out there, such as linear discriminant analysis, PCA, neighborhood component analysis. This is essentially a nonlinear version of neighborhood component analysis. But notice the difference between linear versions and a nonlinear version. And that goes the whole theme of a lot of these models, is that if you're trying to work with high-dimensional spaces, you have a lot of structure in the data, typically the relationship between latent variables and the data is very nonlinear. So you need to go beyond linear models. Okay, so why I stop here, and in the second part of the talk, after the break, we're going to get into more advanced deep Boltzmann machine model, which is quite different from deep belief networks, but has a lot of other advantages than deep belief networks.